Welcome back, everyone. Today we're going to be proving another conditional statement. If n belongs to the natural numbers, then 4 to the n is congruent to 1 mod 3. I should help you with notation. First, we have belongs. This denotes natural numbers. And this here, like an equal sign with another line above it, means congruent. And so the natural numbers is the set of all numbers 1, 2, 3, ... all the way to infinity, and we'll leave it as like that. And so 4, 5, 55, 75, 1,000, 1,005, any kind of number, as long as it follows this form, is natural. Congruency is defined as A is congruent to B mod n, where A and B belong to the integers, and n is a natural number. Right, so A is congruent to B mod n if for all integers A and B and natural numbers n divides A minus B. Right, and so then we also need to go over what the definition of divides means. Well, divides means, so if I have, for instance, B divides A, right, where A and B belong to the integers, if for some k that belongs to the integers, we have A equals B times k. Right, so in this case, it would be A times B is equal to n times k. And I'll denote that here in some brackets. A minus B, make that a big minus, is equal to n times k. So A minus B is equal to n times k for some integer k. And then you can begin to understand this statement. Since the natural numbers are a well-ordered set, it lends itself to using mathematical induction to prove this conditional statement. Mathematical induction is one of my favorite proof techniques simply because it relies on using assumptions that come up and showing things, and I think it happens to be pretty amazing. So, the way induction works is we have a base step. We have an inductive, we have an assumption. And we have the actual inductive step for itself. Right, so in the base step, we look at the first case of our well-ordered set, n. So I'd say, hey, well, is 4 to the 1 congruent to 1 mod 3? By the definition of congruence and divides, 4 is indeed congruent to 1 mod 3. Then I would assume it works for some k, right? Some integer k will say, hey, 4 to the k is congruent to 1 mod 3 as well. I don't have to show that, I just assume it because, hey, it works for 1, it works for 2, it works for 3, it works for 4, it keeps working for 5, 6, 7. So I'm just going to assume for some general sense that it works for k. Next, we have to show the inductive step, which says, well, okay, if it works for some general case, it should work for that case right after it as well. And so we're going to show it works for 4k plus 1, right? If it works for 4 to the 50, it should work for 4 to the 51. And so with that being said, we can go ahead and proceed to prove this statement using mathematical induction. And so I'm going to say begin proof. We proceed by mathematical induction. We know for the base case n equals 1, that 4 to the 1 is congruent to 1 mod 3 because 3 divides 4 minus 1. That is, 3 is equal to 3 times 1, right? Some integer k. Next, we assume for some integer k, I should say for some not integer k, for some natural number k, we're working with the natural numbers. Natural numbers are well ordered, meaning each subset has the least element. Some natural number k, that 4 to the k is also congruent to 1 mod 3, meaning that 3 divides 4 to the k minus 1. So, we've shown the base step, which is right here. We've assumed, and now we need to show the inductive step. So we say, next, we show the inductive step. That is, four to the k plus 1 is congruent to 1 modulo 3. And so after rewriting, we obtain that 4 to the k times 4 to the 1 is congruent to, that should be 1 modulo 3. The 1 should be outside of the parentheses. 1 modulo 3. And I'm relying on a property of algebra that says, for instance, if I have a to the 1 times a to the 2, this is the same as saying a to the 3. Right? If I have the same base raised to a power times a base raised to the power, then I just combine the base into 1 and I add their exponents. And so I'm going to reverse that and say, well, I have 4 to the k plus 1, so then I have 4 to the k times 4 to the 1. Now there's also a property in concerning congruency that's very important. So we know 4 to the k is congruent to 1 mod 3 by assumption. And also 4 to the 1 is congruent to 1 modulo 3, which we showed in our base step, right? And so there's the property in congruence that I'm talking about is if I have A is congruent to B mod n, and C is congruent to D mod n, then A times C is also congruent to B times D mod n. So I can apply that same principle here. I know 4 to the k is congruent to 1 mod 3. I know 4 to the 1 is congruent to 1 mod 3. So then I have 4 to the k times 4 is congruent to 1 times 1 mod 3. Multiplying this out, after simplifying, we get 4 to the k, this is to the 1, so 4 to the k, I combine the base and I add the exponents, plus 1 is congruent to, not equal to, congruent to 1 times 1, which is 1 mod 3. Thus, we have shown the inductive step to be true. inductive step to be true. Therefore, the conditional statement above is true. And this concludes the proof. Thank you very much.